The Kelvin-Helmholtz instability can occur when there is velocity shear in a single continuous fluid, or where there is a velocity difference across the interface between two fluids. An example is wind blowing over water. The instability manifests in waves on the water surface. More generally, clouds, the ocean, Saturn's bands, Jupiter's red spot, and the Sun's corona show this instability. The theory predicts the onset of instability and transition to turbulent flow in fluids of different densities moving at various speeds. Helmholtz studied the dynamics of two fluids of different densities when a small disturbance, such as a wave, was introduced at the boundary connecting the fluids. For some short enough wavelengths, if surface tension is ignored, two fluids in parallel motion with different velocities and densities yield an interface that is unstable for all speeds. Surface tension stabilizes the short wavelength instability, however, and theory predicts stability until a velocity threshold is reached. The theory, with surface tension included, broadly predicts the onset of wave formation in the important case of wind over water, for a continuously varying distribution of density and velocity. The dynamics of the KH instability is described by the Taylor-Goldstein equation, and its onset is given by a Richardson number, ρ. Typically the layer is unstable for ρ and LT, 0.25. These effects are common in cloud layers. The study of this instability is applicable in plasma physics, for example in inertial confinement fusion and the plasma-beryllium interface. Numerically, the KH instability is simulated in a temporal or a spatial approach. In the temporal approach, experimenters consider the flow in a periodic box moving at mean speed. In the spatial approach, experimenters simulate a lab experiment with natural inlet and outlet conditions.